Go to the question. A mild steel wire of length 1 meter and cross-sectional area of 0.5 into 10 to the power minus 2 centimeters square is stretched well within its elastic limit horizontally between two pillars. A mass of 100 gram is suspended from midpoint of the wire. Calculate the depression at the midpoint. So this is the diagram. Let the ends of the steel wire be called capital A and capital B, right? Length of the wire is which is denoted by 2L is 1 meter. The cross-sectional area of the wire denoted by capital A is 0.5 into 10 to the power minus 2 centimeters square, which is given in the question itself. Let the depression at the midpoint due to the suspended 100 gram be Y. Change in the length of the wire is delta L. So delta L is AD plus DB minus AB. So if we put in the value of AD from Pythagoras formula, we know that it is equal to root over of L square plus Y square. So eventually we get the delta y and delta L to be y square divided by L. The strain is delta L divided by y, 2L equals y square divided by 2L square. The vertical components of the tension in the arms balance the weight of the suspended bars. We have 2F cos theta equals mg. So in place of cos theta, we can write y divided by root over of x square plus y squared. So eventually we get the value of F to be mgl divided by 2y. The stress in the wire will be F by A equals mgl divided by 2ay. The Young's modulus of the steel is Y equals 2 into 10 to the power 11 Newton per meter squared, and it is again equals to stress by strain. So in place of stress we can write mgl divided by 2ay, and in place of strain we can write y square divided by 2l squared. So eventually we get the value of y to be mgl cubed divided by ay cubed. So small y is this, and if we put in all these values, we get it to be 1.074 centimeter. The depression at the midpoint of the steel wire B is 1.074 centimeter.